and welcome to episode number 3 of CS350 Online. I'm your host, as always, Leslie Eisted, and in today's episode we are going to continue our discussion of threads. In particular, we're going to look at how do you have multiple threads sharing a single CPU while making the user believe that all those threads are actually executing at the same time. We're going to look at the details of how we actually make that work. We're also, at the very end of the episode today, going to take a look at how to actually debug OS 161. And while that's not going to come into play for your assignment 1, you might find it useful for assignment 0, and you're definitely going to need that for assignment 2. So we'll make sure that you get a little bit of a guide on how to make that work. Before we get into things, there's just a couple of things I want to mention, is that part of your assignment grade is quizzes. These quizzes are all available on Learn. They're all available right now. So if you wanted to go ahead and do the whole course right now, pretty much, you could go ahead and do that. My recommendation to you is not to leave them to the very last possible day, because you want to make sure that you have lots of time to read through the material and actually go through the questions. They're not very long, some are 15 or so questions. It's things like multiple choice, sometimes fill in the blank, and I think in total all of the quizzes together are worth about 10%. So it's if you mess one up, it's not big, but still do. The other thing I wanted to just remind you is to introduce yourself on Piazza, and I know a few of you have done that. I know not everybody likes to be social, so no pressure really, but if you do want to introduce yourself, do try to do so soon. All right, so our operating system of the day today is one called Exec1, and again, I'm not going through every operating system from the perspective of here's every operating system that's ever existed. We're only choosing the ones that had something interesting about them. So Exec1 was released in 1962 for the UNIVAC 1107, which is in the picture below. This picture is actually nice in color. And what you can see here again is you've got some magnetic tape drives. That's hard drives, storage, permanent storage. And then you've got some computation units and some operator consoles here. It's actually a pretty sparse room, but there's probably lots of things here you're not seeing, like this back wall is actually all part of the computer as well. Now, this operating system was not much more than the previous one, except it had one big thing that the previous operating system didn't have. So it was a batch processor like its predecessor that we talked about. Sorry, I'm scrolling the wrong direction. GMNAIO, but what this operating system also offered was multi-programming. And if you remember, we actually talked about multi-programming in our last episode, where we mentioned that multi-programming is the concept of when your CPU is sitting idle because you're doing an I/O operation, or you're interacting with like a printer or something, some kind of operation that it doesn't involve the CPU would sit idle. And that is a lot of wasted money, especially back then when computers were millions of dollars and there were very, very few of them. So they got the idea of when the CPU is idle, we will run a different job. And so this operating system actually has support for multi-programming, which is pretty cool. Now, it actually had a lot of other interesting things. So it actually had solid-state memory. Yes, you heard that correctly. So this concept of a solid-state disk, which we think of it as something that came about in the early 2000s, it's not actually new at all. That style, although it looked very different, obviously, that concept of having solid-state memory, like persistent storage, that doesn't use moving parts, has actually been around for a really long time, and this machine actually had it. So that's pretty cool. One of the other things that made this OS a little bit on the popular side was its optimized Fortran compiler, and it had a cool assembler with macros and a really flexible linker and loader, so it actually made it, for the time, a fair bit easier to work with. One of the really bizarre quirks about this particular machine is that its word size, we think of words as being powers of 2. So, the previous generation of computers, our words were 32 bits. So, yeah. And then now our words, we think of them as 64 bits. Well, words on this machine were 36 bits. And the machine could store 65,000 of them. So in total, this machine had about 288 kilobytes of memory. I mean, that's not including these tape drives here, because these tape drives are your secondary storage, but That means like the actual amount of machine memory it actually had, which was probably one of these giant units, actually. So there's a question on Twitch here that asks, why did it take until the mid-late 2010s for SSDs to be popularized? So you're looking at the 1960s ones. I could probably stand in them. They're huge. They're big, big things. And they didn't actually work that well. And then if you look at the technology was really, really expensive and really, really large, and it didn't come very far. So there wasn't a lot of progress made on it for many, many years, because things like punched cards and punched paper tapes and magnetic discs were cheaper and more reliable. And then when you get into the 90s, people start realizing that this is actually, and laptops start to become really, really popular. People are moving around hard drives, which are physically moving pieces of glass. Maybe we'll talk about that another day, months from now. They're really fragile. And so SSDs, they start coming back. And I'm going to say the early 2000s ones, again, they were really, really expensive, really, really small, and not really reliable. Like, I remember I bought one in 2007, and they had a 35% failure rate. 35%! And the bad thing about that is that you can't recover the data off of the suckers. Unlike these magnetic drives where you can. And then now, as technology, we've improved, now they've come down a lot in price because the tech has been easier to produce and it's been a lot more reliable, which is really nice. Yeah. SSDs, if you have a laptop, you want to have an SSD in it. I'll tell you that. Because an SSD actually doesn't have any physical moving parts. It's just a bunch of circuits, like chips on a board. Whereas an actual hard drive, even the 2.5-inch, if you were to open it up, and please do not do that, that's a really bad idea. If you open it up, there's actually physical moving parts. And not only does that require more power to drive it, because it has to actually spin up multiple motors to make it work, but it's much more, it's very fragile and it's more susceptible to damage and wear and things like that. It's not to say SSDs can't fail, but because they can, and they still can, but we'll talk about those in greater detail another day. All right. So this is our OS. Just a brief then recap of where we left off. So we left off talking about threads and concurrency. I always scroll the wrong direction. If you're wondering, why is she always scrolling in the wrong direction? So here's the thing. Apple's default scroll is like backwards to everybody else's. And when you have as many computers as I do, and they're all running different operating systems, you forget which direction you're supposed to scroll. My daughter's actually using my old Apple, and I actually switched the scroll direction because she usually uses a Windows machine, so I made it mimic that. I should probably do the same. Too lazy. Anyways. So we were talking about a thread. So remember that a thread is just a sequence of instructions. And in order for a program to actually execute, you have to have a sequence of instructions. Without a sequence of instructions, you have no assembly in which to run. So every program has to have at least one thread. And every program that you've written as a part of your undergrad career, so the courses would have been usually probably just one thread up to this point. Now, what's really interesting is we use threads for lots of different reasons. The obvious reason that we use threads is because we want to improve the utilization of our CPU, so this concept of multi-programming, never letting the CPU become idle. And the other big reason that we tend to use threads is because we want to improve parallelism. We actually want, by dividing programs into multiple threads, we want those threads to actually be able to execute truly in parallel. And the hardware that we've had since about 2003, by default, has supported this. So I had, was it a Pentium 4? I don't remember. My first laptop that I actually bought, which died in flames, like actual flames, came out of the keyboard. That machine had a hyper-threading. So that was kind of the first of that era of a single CPU that could actually run multiple threads. But nowadays, everything has at least 2 cores, which means you are running at least 2 threads in parallel. When you have parallelism, you have instructions executing simultaneously, which means you are improving your performance, which is really, really nice. Now, other reasons why we might express things in terms of threads, things like modularization. And this is one that people don't think about a lot of, but sometimes your code does a lot of different tasks. And it would make more sense if you modularized your code such that this is the thread that handles rendering, and this is the thread that handles the AI, and this is the thread that handles the user's responsiveness. So it makes sense to modularize the code quite often. We talked about how to create threads in OS 161. So their threading library is actually very restrictive. You have thread fork to create a new thread, and you can attach it to a particular process or a program. And the sequence of instructions that you're passing it is this function pointer, because the function is a sequence of instructions. We can terminate a thread voluntarily using thread exit, and if we want a thread to voluntarily give up the CPU, we can use this function called thread yield. But thread yield is not explicitly necessary in your own code. This is something that you would use very rarely as like a user developer. In the kernel, there are definitely places where this is very useful, but as someone developing on the outside of the kernel, this is something you don't use very often. And if you're wondering, why don't people use thread yield very often? There's no guarantee that if you call thread yield, that you will actually give up the CPU. And the reason is there may not be any other threads. There may not be any other threads of higher or equal priority. Every other thread that is in the system might be busy right now and not ready. So with thread yield, there's no guarantee you're going to give up the CPU. So if you're using thread yield because you think you're going to, oh, my CPU is running really hot, I should probably pause this program momentarily so that the CPU can cool down, I'll use thread yield. Don't use thread yield for that purpose because there's no guarantee. If you want to cool your CPU off, use sleep, because that will actually put your computation-intensive thread to sleep. Sorry, that might seem like a very strange thing that you might want to do, but in computer graphics, if you're doing some kind of really compute-heavy rendering thing and you're doing it on a laptop and you don't want to set it on fire, sometimes it's good to have periodic sleep so your CPU can cool down. And yes, I put those in my own code. I've set enough laptops on fire, so I don't need to do it anymore. And I wish I was joking about the laptops on fire. I'm actually not. All right, so OS 161's threading library was very limited, and as I said, there are other threading libraries out there that you should get some experience using. Assignment 1, we are going to have you use this library right here, pthreads or POSIX threads, to solve a couple of very simple problems. And the reason why we've switched assignment 1 over from getting new experience using threads in OS 161 to giving you experience using threads in the real world is because presumably you're all applying for co-op jobs, and it would be really nice if you had some real world experience with threading that you could carry forward into your CV and your interviews and future courses. So we've decided to switch that assignment over to pthreads. And then if you like lazy threading, there's OpenMP, which is my personal favorite. And then, of course, if you really want to do hardcore multi-threading, you can write code for your GPU. This is a little tricky, though, I will tell you. So as someone, I've done a lot of work with CUDA, which is NVIDIA's library for this. And it's really different. So you might remember like a time in CS 135 or 136 where you weren't allowed to use conditional statements or if statements. And that's actually how you want to write code for these things. So it's all this weirdness that you thought was just silly in 136 or 135. Why can't we use this? There are actually reasons why you might want to write code without those conditional blocks. And it's for GPU programming. And if you want to know more, feel free to ask on Piazza. All right, so we reviewed the basic registers and things like that. You can refer back to this if you need to, but remember that you are not in this course going to be asked to write any assembly code on any of the assignments. So if you don't quite remember the instructions for add or what particular registers do, That's not a big deal, although you will note that the named registers are kind of important. And then we talked about how do you implement this concept of concurrency, where you have either threads truly executing in parallel or the illusion of threads executing in parallel. And we mentioned hardware support, which is very common, but the number of threads that your computer is running today is so large that that on its own isn't enough. And if your hardware then doesn't support anything, you can do this concept of timesharing, which is rapidly switching between the threads that are running. And of course, our modern machines are actually doing both. And where we're going to focus our time today is looking at this concept of timesharing. How do you get multiple threads to share a single CPU? All right. So question on Twitch is, what is the difference between a thread and a process? So a process is the whole execution environment for a program. So it's the address space, an array of threads, some other connections to different things like the file system. But a thread is just a sequence of instructions. So a process cannot be executed unless it has at least one thread. But a thread on its own is not really it's just a sequence of instructions. Whereas the process is the whole program with the address space and all the other threads and the connections to the file system and so on and so forth. So it's the whole program. All right. So the concept of time sharing is kind of a funny one. And what we want to do is we have one CPU or a fixed number of CPUs, and we want to make sure that each of the threads is going to get its fair share of time executing on that CPU. And when we're doing this, we want to make sure that the user is not aware that only one program is running at a time. Because one of the ways that you could do this is you could have thread A completely execute, and then thread B completely execute, and then thread C, and then thread D. That would be very fair. Everybody takes a turn. You go in the order that you arrive. But the problem is, to the user, if you're trying to watch 2 YouTube videos at the same time, the equivalence of that would be one YouTube video plays and then the other YouTube video plays. And I know a lot of you are like, why are you watching 2 YouTube videos at the same time? Well, because I have multiple screens and my 2-year-old's sitting beside me, and I really don't want to watch the ABC song for the 100th time. So I'll have a different YouTube video open on closed caption or something. So what we want in reality is the threads to do a little bit of work and then switch and let another thread do a little bit of work. And we want this switching to happen fast enough that the user has the illusion they're actually working at the same time. And this is what the concept of time sharing is. And there's this word we use to talk about when we're switching from one thread running to another. And we call that the context switch. So the idea of a context switch is the one thread is going to stop. And when it stops, we need to choose another thread to run, load that thread, and let it go away on it about its business. But there's a few things that has to happen first. So first thing is on a context switch. So when we have stopped the running thread to say, hey, you need to give up the CPU, we need to decide which thread is going to go next. And that's this concept of scheduling. And we'll talk about it down the road. Now, we want to make sure that the thread that we have stopped, when it does get to run again, it continues at the exact point from which we stopped it. We don't want the thread that was running and stopped to ever know it was stopped. So we're going to save all of the contents of the registers for the current thread because that's its current context, its current state. And then to load the new thread or the other thread we're going to be running, we're going to load its context or state back onto the CPU so that it can be run. Now, there's a question on Twitch here about assignment 0. There's an error message. So I have pinged our ISC who sets the system up, and I am hoping that gets resolved very quickly. But I don't recall when I set the due date for that assignment. So just give me a brief minute here to look that up. So when is that assignment due? Okay, so that's due on Friday. So hopefully we will have that fixed today. I will ping our ISC again to make sure that gets up and running. So don't panic. And if it doesn't become available by the time the deadline is, obviously we will do something to compensate you for that. Please do be patient with us. As I'm sure many of you have seen, there have been a number of changes to the school servers, and a lot of things have kind of broken. So we're trying to do our best to find what has broken and get it repaired, but it is taking a little bit more time than we expected. But don't worry. Either we'll compensate you for A0 in some way by extending its deadline or just scrapping it. Or we'll get the dang thing up and running. Hopefully we'll get it up and running as quickly as possible. So please do be patient. And I will ping them again to make sure that things are working. Because I do want you to submit A0. And the reason why I think A0 is so important is because it's making sure you actually get the operating system running and you get it compiling and executing for at least that first try. So I do think A0 is really important. But anyways, either way, don't worry about it. We will get it fixed or we will compensate you in some way. Okay. So we've talked about now this idea of a context switch. But here's a really interesting question. How do you force a thread to give up the CPU? Just keep that in your mind as we're going through this. So there's two levels to the context switch code. There's kind of a high-level context switch, and I'm actually going to switch over here to, I'm on the wrong thingy again. There we go. Lots more space. Now you can see it nice and big. Nobody needs to see that. So let's go over into OS 161's code. And let's see, I'm going to include directory. So I'm going to go into thread, and this is kern, and inside of thread I am going to open thread.c, and I'm going to go down to thread switch. I can't spell. Excuse me. There we go. So this is kind of the high level context switch code, and what's going to happen in here, you'll see these things about disabling interrupts, because when we're doing this task, we don't want to be interrupted. We'll talk more about that at a later date. But then what we're going to do is we're going to find out which thread runs next. So we're going to run the scheduling algorithm. And there's some thread-based optimizations. And then once we have our new thread that we're going to run, then we so this is doing some high-level optimizations and choosing the next thread to go. Then we're going to call, so that's the high-level context switch. Then we're going to perform this low-level context switch. We're going to call this function called switch frame switch. And this is the one that's actually in the slides. And it's actually written in assembly. So what this code does is it's going to take two arguments, which is the address of the stack for the old thread and the address of the stack for the new thread. In the first half of this function, it's going to push the state or the context of the current thread onto the current thread's stack. Now, the context is every register value. And what you'll notice here is that we're only doing the S registers, the return address, and the global pointer and the stack pointer. What about the T registers? Well, you don't need to save those, because the T registers, if you remember, scroll the right direction here, let's go back here, are caller save, which means that the high-level function thread switch has already saved all the T's for you, which means all you need to do in switch frame is save the S's. So you need to save the callee save registers. Once you've saved the callee save registers and you've pushed that all onto the stack, we can now save the old thread stack pointer onto its stack. And now we are ready to, so our context for the old thread is completely saved. Now we can store load the contents of the new thread's context. So we're going to switch to using the new thread's stack pointer, and we're going to load the callee save registers from the stack onto the CPU. Now you'll note we are not loading the caller save registers because this function returns to thread switch the caller, and the caller is responsible for saving and restoring the caller save registers. So the T registers will be saved and restored by thread switch. So we've loaded our callee saves and our global pointer and our return address, and we have popped them off the stack by adjusting the stack pointer here, and then we are jumping to the return address. And the return address we are jumping to is going to be in the new thread. We are returning to thread switch in the new thread so that it can restore the caller save registers. Now I want to point out a couple things about this code. There's nothing in particular interesting on the first slide. But on the second slide, if you don't remember much about assembly and pipelined machines, you might have forgotten that while this instruction is loading and executing, the next instruction enters the pipeline. Now, tasks like this load operation take more cycles to complete than an add operation. And what that means is that the result of loading the stack pointer into the stack pointer register will not have completed by the time we try to use the stack pointer register in the next instruction. So, and this is because of pipelining and because loads and stores actually take a really long time. Things like jumps as well. So we have these things called delay slots. These are operations that we put between where we load something and then where we use it, or wherever the next pipeline instruction would execute before the previous one finishes. So in this delay slot, we've put a NOP. A NOP is a no operation. It's an assembly instruction that does nothing. You don't always need to use NOPs. Sometimes you can be clever and rearrange your code such that maybe you have an add operation here that doesn't use the stack pointer, and you could put that there. But in this case, there wasn't, so we had to put a NOP here. Now, they have put a NOP here, but there was no reason to, so if they had just switched these two instructions here, these two loads, they wouldn't have needed the NOP here. Not everybody's perfect, right? But there's also a delay slot for the jump. So while we are executing the jump instruction, the instruction that follows it is loaded into the pipeline, and it's going to execute as well. So we've put our popping of the register values off of the stack. I'm moving the stack pointer. We've put that in the delay slot for the jump instruction. So the question on Twitch is, why isn't there a NOP between all the loads in the middle? So each of these. The reason is that they are loading from the stack pointer. At this point here, the stack pointer register is loaded and correct. And we are loading from an offset of the stack register. That's what the number before the SP represents. So this is SP plus 0, this is SP plus 4, this is SP plus 8, and so on and so on forth. And we are loading into different registers, and we are not using those different registers in the subsequent instruction. So we are not coming up against an issue where the previous load is not having completed will impact the next one, because we are loading into separate registers and we're not using those separate registers. So we don't need any NOPs here. That's totally fine. All right. There's a little bit more of an explanation of this for those of you who like to read on the next slide, but I'm not going to go over that. All right. So let's think about all of the different things that actually cause these context switches now. So we know that if we call thread yield, we are voluntarily giving up the CPU. And if we're giving up the CPU, that means that the CPU, not wanting to be idle, will need another thread to run. So when we call thread yield, we get a context switch. Obviously, as well, by that same logic, if you call thread exit, you are terminating the running thread. We don't want the CPU to sit idle. And so in this one, we are also going to have a context switch when we call thread exit. Then there's two that we haven't really talked about. Well, we've talked about one of them, but not the other. What if a running thread blocks? Now, what does that even mean? Well, it means the thread that is running needs to wait for something before it can continue. So, for example, maybe you want to put the running thread to sleep for 20 minutes. They're due for 20 minutes. That's awful. But if I put a thread to sleep, it's no longer using the CPU, which means the CPU is now idle, which means I need a new thread. So when a thread blocks, and in OS 161 it does so by a call to this function here, then what's actually going to happen is a context switch. And the final one is this idea of preemption, which is the time-sharing operation. This is where a thread involuntarily stops running so that another thread gets a turn at the CPU. So these four reasons here are why we get context switches. And we could draw this as a lovely state diagram where you've got ready threads. These ready are all of the threads that could execute instructions right now, but aren't. And when there is a context switch, one of the ready threads will move to running. If you are preempted or you yield while running, you go right back to the ready pool because you didn't stop because you wanted to. You were either voluntarily giving up the CPU, you're not waiting for anything, or you stopped because you were not given a choice. If you are stopping because a resource is not available, you go down here to the blocked thread pool. And they're in a separate pool because they're not ready. They're waiting for something. And they can only move from blocked to ready if one of the running threads wakes them up and moves them there. All right. So what does the stack look like if we have a voluntary context switch? If you have a voluntary context switch, it's very simple. We call thread yield. Thread yield is going to force the context switch, and so we call thread switch, and then switch frame. So that is what our stack looks like for a voluntary context switch. What about those involuntary ones? So here's the issue. Many, many years ago, the concurrency for macOS and Windows was actually implemented by something called Cooperative Concurrency. And the only way that threads could actually share the CPU was if they were good about it. That is, they either blocked, waiting on a resource, they terminated, or they were kind and voluntarily yielded the CPU. Hence why it's called Cooperative Concurrency, because the only way that you can share the CPU is by voluntarily giving it up, blocking to wait for a resource, or terminating. The problem, of course, with cooperative concurrency is that it relies on the user to actually write their programs with yields built in so that they could actually share the CPU. And this is how concurrency was implemented in Windows and how it was implemented in macOS for a very long time. I think from about the mid to late 80s all the way through to like 2000. And it wasn't until we switched to Windows 2000, which is part of the NT family, and it wasn't until macOS switched to macOS X that they actually switched away from cooperative concurrency. And you might be thinking to yourself, why on earth did they do that? Why would they not have proper time-shared concurrency? Because at the time, it wasn't a big deal. Because at the time, processors were really bad. My first computer was a 1981 IBM PC. I think the processor speed on that was 4.7 megahertz. Not 477 megahertz. 4.7. Okay? And then I got like a 386. And then a 486. These computers did not have a lot of processing power. Their clock cycles were really slow. You didn't have a lot of memory. So my first computer, the 1981 IBM PC, I actually had a RAM expansion board. I don't remember, it was like Quad RAM, that was the name of it. It was a Quad RAM expansion board. So instead of having the default 64 kilobytes of RAM that you got with the machine, or maybe it was even less than that, I actually had a 256 kilobyte expansion board. And do you know how big that expansion board was? Can you get it on camera here? It was about that big. It was so big that it actually hung out the back of the computer on purpose. Like that was its design. It actually hung out the back. It was massive. And when I had 486s and low-grade Pentiums in the 90s, I only had like 30 megs of RAM. I think the most RAM I had until like 2003 was like 512 megs. And 512 megs was like, oh, you have like a supercomputer. The point I'm trying to make is that the idea of time-shared concurrency, even though it existed and people did it, just not in those operating systems, for consumer-grade hardware and for the things that consumers were doing, it didn't make a lot of sense. So these operating systems were actually able to get away with cooperative concurrency for a really, really long time. But how do we implement time sharing itself? How do we make a thread give up the CPU when it doesn't want to? I'm assuming I have one CPU. So it's not like there's another thread that's counting, okay, so many seconds have elapsed. You have to give up the CPU. You can't do that because there's only one CPU to execute on. You can't have two threads. Sorry, Twitch comment, blackmail. That's a good one. So how do you force a thread that is using 100% of the CPU to get off the CPU? We call this act, by the way, preemption. We are involuntarily kicking you off the CPU. So you can't get control of the thread from another thread. Blackmail doesn't work either because, it's a thread, it doesn't have feelings and things. How we actually do this is really interesting. We're going to use interrupts. We're going to use our hardware to stop the thread. And the particular device we're going to use is the clock. Yes, your computer has a clock device in your computer. And it is responsible for booting threads off the CPU, amongst obviously telling you the time and various other things. So just a review of interrupts. So interrupts specifically are caused by hardware. They are signals that hardware sends to the CPU because something happened. Hardware is generally not intelligent enough to figure out what should I do now that I am done the task you asked me to do. So for example, we would get an interrupt. This is just the first device I have that's small I can pick up. This is a Wacom tablet, and it's got a bunch of buttony things and a pen, obviously. So if I were to push one of these buttons, that would create an electrical signal that goes from the device to my CPU to say, a button was pushed, but I don't know what to do. What should I do? Now, it might change a state internally here, but we need to inform the operating system that something has happened as well. And so that electrical signal goes to the CPU. Now, the CPU doesn't know what to do with it either. The CPU's job is that fetch execute loop. The CPU's job is not to figure out why did the keyboard throw me an electrical signal. So what happens when the CPU receives an interrupt is it stops whatever it's doing. And it says, okay, a device needs something. I don't know what they need, and I don't care what they need, but a device needs something. And the only person who knows what to do with this is the kernel of the operating system. And so the kernel of the operating system has this thing called, in memory, called a trap table. And the trap table contains the address of a generic interrupt handler. Because at this point, we don't know what device threw the interrupt. We just know somebody threw an interrupt. CPU doesn't care who. So what happens is the CPU stops executing whatever it is it's doing. And then what it's going to do is it's going to immediately start executing the interrupt handler, the generic whose address is located in the special place in memory called the trap table. And in the generic interrupt handler, we do several things. The first thing we need to do is we recognize the fact that the CPU just stopped executing some thread. And that thread probably didn't want to be stopped. And we need to be able to let it continue from where it started off. Can you imagine if you were watching a movie in VLC and you pushed something other than the space bar and it caused the movie to pause? That'd be really annoying, right? Like, it didn't just cause the movie to pause, it actually caused VLC to shut down. That would be awful. So we need to preserve the state of whatever was running on the CPU before the interrupt. So in something called, in the generic interrupt handler, the first thing we do is we need to save the context of the running thread. And we create what's called a trap frame, where we don't just save the S's or the T's, we actually save every register, including the special ones. And you're like, special registers? Low and high. All right. Once you've saved the trap frame to the stack of the thread, then the generic interrupt handler can actually go about its business and figure out which device threw this interrupt, and therefore, what do I need to do to handle the interrupt? And we are going to hijack the system to preempt our threads and cause context switches. So there's another question on Twitch here. Why does hardware have to do it? I can do it using Control-C from a terminal. Well, when you type Control-C, you're actually firing an interrupt. And that interrupt is going to cause the thread that is running to stop. And then the generic interrupt handler is going to run. We'll save the context of the current running thread. And then in the kernel of the operating system, we'll recognize the fact that, oh, you pushed Control-C. I know what you want to do. You want to terminate the running thread. And then the kernel of the operating system will do that task for you. But in order for Control-C to actually stop the software from running, we're still firing interrupts because we're pushing keys on the keyboard. So the kernel is still involved here, and so are interrupts. All right. So let's look at this from a stack perspective. We're going about our merry business, blah, 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 and all of a sudden we get an interrupt. The first thing that goes on the stack after the interrupt is the trap frame, and that is the complete context. Every register is saved. And only at that point can we run the generic interrupt handler to figure out what we should do next. So we want to stop the running thread. We're trying to preempt it. We've managed to stop it. We've regained control of the CPU. We're in the kernel. The question is this a context switch or not? So how do we decide how often we should force a thread to stop? So we have this thing called a scheduling quantum. And the question on Twitch is every register, both S and T, S, T, A, V, the kernels, all registers 0 through 31, plus low and high, and some of the other fancy registers that we don't even talk about. Everything gets saved. So we have this thing called a scheduling quantum, and this is the time limit in which a thread is permitted to use the CPU for. So if we set a time limit of 20 milliseconds, then after 20 milliseconds have elapsed, the clock will fire an interrupt, and the thread must be kicked off the CPU. It stops running because of the interrupt, and then in the interrupt handler, we will force a context switch. So the scheduling quantum is the time limit. It's the maximum amount of time a thread is allowed to use the CPU per turn. If you terminate, if you yield, if you block before your quantum is up, there's no concept of keeping the leftovers. What we are going to do is whatever thread run next, it gets a brand new quantum. And the next time you run, you get a brand new quantum. So there's no sharing, there's no leftovers or anything like that. Each time you get a turn to run, the scheduling quantum is the maximum amount of time you're allowed to use the CPU for. And what we're going to do is we're going to tell the clock device to do a periodic countdown. Now, some clock devices, each time there's a context switch, we will restart it and say, okay, this thread now gets 20 milliseconds. Please start me a 20 millisecond countdown. It's one way it can be done. The problem is you end up talking to the clock a lot more than you want to. So another way that people actually do this is they will set a countdown for a smaller unit of time, like 5 milliseconds. And then each time there's each time the 5 milliseconds finishes, the clock device fires an interrupt, and in our interrupt handler, we'll check, has the current thread exceeded its scheduling quantum? If so, force it a context switch, and if not, let it keep running. So there's two different ways you can kind of implement this. Needless to say, if the thread has exceeded its scheduling quantum, we are going to force the context switch. And to force the context switch, we call thread yield. Because we don't want to put the thread to sleep. It doesn't want to sleep. It's not waiting on anything. We are involuntarily booting it from the CPU, which means thread yield is more than sufficient. So our trap frame goes onto the stack first, immediately after the interrupt. Then we have this generic interrupt handler. And by the way, we are going to fill in. There's a lot of things that happen in this turquoise block. We will fill that in when we talk about processes in a few weeks. The timer interrupt handler, which is the interrupt handler for the clock when its timer goes off, will then realize, hey, your scheduling quantum has expired. Okay, you need to get off the CPU and somebody else needs a turn to go. So we're going to call thread yield. Thread yield calls thread switch, and thread switch calls switch frame. Now remember, this isn't a guarantee. Even if you get booted off the CPU, what if there's no other threads? What if there's no other threads that are ready? You may still get to go again. And there's some optimizations, by the way, that happen in thread switch, such that if you are the thread that would get scheduled to go next, switch frame wouldn't need to run because we don't need to save and restore your own state. All right. So I'd like to show you a little bit of an example. And I'll do that after I answer this question on Twitch here. So the question on Twitch is, what if a thread has exceeded its scheduling quantum, but it's in the middle of a very important task? Does the interrupt handler acknowledge that and wait for the thread, or does the handler just cut it and leaving the thread to deal with the consequences of its actions? Okay, so the kernel of the operating system has no idea what the threads are doing. So there's no concept of the thread exceeds its scheduling quantum, the kernel realizes the thread is doing something really, really important, and therefore we're going to let the thread go back to its business. There is a way we could kind of represent that, and that's by setting the priority of the thread. So if you were the highest priority thread in the system and nobody even came close to you, there is a good chance that you would continue running after the quantum has expired. But there's usually a lot of threads that have the same priority as you because they're interactive threads. That is, they're interacting with things like the mouse and the keyboard, video games and things like that, web browsers. So that's not going to happen. Keep in mind, the kernel really doesn't know what your thread is doing. And a thread can't stop the context switches from happening. Like, a thread cannot stop the quantums from expiring. It can't do that. And you wouldn't want it to, because how do you determine that one thread's job is significantly more important than another, right? So we do, and the other thing to keep in mind is, from the thread's perspective, even though it gets kicked off the CPU, it's not really aware this is happening. Threads don't have some kind of awareness. It's executing, it's executing, it's executing. It stops executing and its context is saved. And then when it gets to execute again, because the context gets reloaded, it's as if nothing happened. So even if it was doing some important job, the little time that it was kicked off the CPU for, it's almost as if that didn't happen. But again, if we did want to reduce the chances of really important threads from being booted off the CPU, we would give them really high priorities. OS 161, by the way, does not have priorities for threads. Every thread has an equal priority, and we do this thing called a round-robin scheduling, which is just an extension of first in, first out. So there's no concept of that in OS 161 priority. But in the operating systems you are using right now, there absolutely is a concept of priority. So in any Linux kernel-based operating system, they're using something called the completely fair scheduler, which proportionally divides up a CPU's time according to the thread's weight. So the higher weight you have, the more CPU time you will get per block. And then macOS and Windows use something called multi-level feedback queues. We'll talk about this in scheduling, by the way. And multi-level feedback queues, the goal is to try to identify automatically which threads are interactive. And an interactive thread is considered a thread that blocks frequently or is very, very short. And a blocking frequently thread is things like a game, because it's always waiting for you to push a key so that it can move to the next game state. And so higher priority, significantly higher priority, is given to interactive threads as opposed to things like BitTorrent that's sitting in the background, or your ray tracer that's sitting in the background. So they prioritize based on interactivity, which makes a lot of sense. So another question on Twitch is, wouldn't all of these interrupts slow down the overall computer if the CPU is frequently switching to the kernel? Yes! Yes, it does. So there is a cost to a context switch. Context switches are not free. They need to be very efficient, though. So we need to make sure that however a context switch is implemented and all of the subtasks that are a part of it are as quick as possible. So things like your scheduler, which chooses which thread goes next, needs to be super, super fast. So you don't want to have to do a linear time search or worse to find which thread is appropriate to go next. Having like a constant time operation to figure out the next thread, yeah, we want that. The other thing too is you want to minimize whatever work is happening. So yes, these context switches are going to slow things down, but not really noticeable. I mean, back in the 90s and the 80s, it would have been a lot more noticeable on consumer grade hardware. And when timesharing came around in the mid to late 60s, it was much more noticeable then, but that's because it was 1960, right? So yes. So another question here, what would happen if there was not enough memory available on the thread stack for the context switch saving? Yes, and we will address this actually. So every thread actually has two stacks. There's something called the kernel stack where this would actually get saved to. It's things that are kernel. And then there's the user program stack, which is kept separately. That way, kernel operations don't cause the program stack to overflow. And since the kernel stacks are usually very, very small, there won't be an issue there either. So it's a security and an overflow thing that we keep the two stacks separate. We'll talk about that more in processes. How many interrupt handlers does the CPU have? What about the trap frame? This is really hardware and OS specific. So, I mean, the number of different interrupt handlers that your operating system has is going to depend on the OS, number one. It's number two, going to depend on you, actually. So, for example, my default MacBook, if it just was my MacBook, there would be significantly fewer interrupt handlers. However, I have a giant 38-inch ultra-wide plugged into it. I have this 4K webcam plugged into it. I have my microphone plugged into it. I have a mouse plugged into it. I have my tablet plugged into it. I have a wired internet connection plugged into it. So the number of interrupt handlers that I have is going to be significantly more right now than I would have if I was, say, using the laptop upstairs, just as like on battery. Now, we have one, OS 161 actually just has one generic interrupt handler. Most operating systems have a generic interrupt handler and a generic exception handler, so one of each. And then the generic one's job is to figure out which device did it. And then they would call the specific handler based on that. And another question, now, so for the part about the trap frame, you don't need multiple versions of that because its goal is to save the state. So save everything. You only need one copy of that. When you get a new device and you have to download drivers, does it add to these interrupt handlers? Yes, it does, actually. So when let's say you were to buy something new for your computer. I don't even know because I have so many peripherals at this point. I guess maybe a joystick is something I don't have. I really like using joysticks, to be honest, but let's suppose that you bought a joystick for your computer and you plug it in. If your operating system doesn't already have the driver for that, and these days they have the drivers for practically everything, you are going to need to either manually install it or have the operating system go and find the driver for you. And that driver will contain appropriate interrupt handlers for that particular device, and they get integrated into loadable kernel modules, which we'll talk more about another time. Okay, so we've got about 15 minutes here. I think I'm actually going to skip this example for today. We will actually use this example here as review for Thursday's episode. And what I want to do, the reason why I want to skip that is because I really, really want to show you how to do debugging in OS 161, because I think that would help a lot of you. So, hope my computer doesn't do anything silly. So the first thing I want to say is before you do any debugging in OS 161, there is a very, very important thing you need to know. You need 2 terminal windows, and both of those terminals must be on the same machine. So if you're logging into the school servers to do your assignments, which at this point I'd actually kind of recommend, because getting OS 161 to compile on your natively on your own computer can be a big pain. I know a student has put out a few Docker images, and you're welcome to use those. And I've put out some patches and stuff to make it work with like DCC 10. It's still not fun. Sometimes it's just easier to use the school server. And if you are using the school server, the thing that you have to pay critical attention to is the fact that you have to log into the same specific machine. So look up the machine names and log into the same one. So I obviously am not running on the school servers. So I always get booted off after like 30 seconds. You're not the only one. So I've got 2 on the same machine here. It's my local machine. And both of them, you'll see, are actually in the same directory. So we're in the root directory. And in order to run the debugger, what we are going to do is... I always forget this command. That's why I'm sitting here like, where is my command? I don't memorize strange Gdb commands. I don't know. Does that make me a bad person? Just searching through my notes to find it. Oh, there it is. Okay. So what we're going to do is in the first terminal window, this part I do always have memorized, we're going to do sys161, and we're going to use the W flag. And the W flag is going to be used to wait for the debugger connection. So use W and then kernel. Oh, that's some bad spelling. And that's what I'm going to type in my first cell. Now, what you'll see here is it says waiting for a debugger connection. And this is at the point where you go to the other terminal, and you're going to run GDB from here. Now, make sure you are running CS350 GDB and not regular GDB, because even though regular GDB does have support for MIPS, it does not have support for the specific simulated MIPS CPU. So use our variant of GDB. What you're going to type into this terminal is CS350 GDB. So for those of you asking on Twitch, how do you log into a specific machine? You need to go into the CSCF website and look up the machine names. They actually have a list of them. It's like Ubuntu and then the version and then a number. And you need to just, instead of logging into the generic linux.student.cs, you need to actually replace that with the machine name. So that's how you log into the specific machines. So in this one, you're going to do CS350 GDB, and it's really important you specify which binary you're running on. So this would be the same one I'm running in the other window. So CS350 GDB kernel assignment 0. So I typed that. Nothing has changed See? We're still waiting for the connection. These are the commands that I always forget. I had to flip through my notes here for. And we need to tell GDB where the code is and where the binary is, and then we need to actually connect GDB to the waiting simulator. So the first thing we do, and you could put this in your GDB init file, I would almost recommend it, is you do tell it where to find things. So directory, OS161, kern, compile, ASST0. Or you could just type this each time you log in, of course. Okay, so now GDB knows where all the source directories can be found. So the next command is what we are going to do to connect GDB to the simulator. So target, remote, Unix, sockets, GDB. And I always mistype this. There we go. Okay. So you'll see here, we are now connected. And if we go over here to Sys161, it has recognized that the debugger has connected. But OS161 hasn't started yet. If I hit C in GDB, OS161 will start, but I'll lose control of GDB because there's nothing telling to give GDB control back. So if I want to place any breakpoints, I want to place them before I actually start executing. So a breakpoint is something that says, when you reach this line of execution, pause execution so that I may explore what is going on. So I am going to put a breakpoint, and I'm going to use the letter B for breakpoint, and I'm going to put it in the file threadtest.c, and I'm going to put it on line 64. And you'll see that it recognizes breakpoint 1 is at this address in this file and this line number. Okay. Now that I have this breakpoint, I could add other breakpoints. So that's one way. Specifying the file and line number is one way that we can actually add a breakpoint. There's another way that you can add a breakpoint. Let's say you want to add a breakpoint for the panic function, because you guys are going to get lots of kernel panics. And if you want to know where the kernel panic came from, you need to be able to trace back from the panic. So another way you can add a breakpoint is B panic. So B and then the function name. So breakpoint 2 is at this address in kprintf line 150, and that's where you'll actually find the implementation of the panic function. So that's cool, right? Okay, now that I've placed my breakpoints, I am going to continue execution, so I hit C. And now you'll see I've kind of lost control of GDB, and that's because if I go into the other terminal, OS161 has started running. Now, I don't want to start a kernel panic right now, but what I do want to do is I want to run thread test 1, which is where I put my first breakpoint. So TT1. And you'll notice it says starting thread test, and then it stops executing. Well, it stops executing because if I go over to GDB, I see that we've hit the breakpoint. And when we hit the breakpoint, it tells me you've hit a breakpoint. This is the breakpoint. What code is at that? The function that it is in, here's the parameters that were passed through. And now there's a bunch of things that I can do. I can do this command called list. And what list does is it shows me a few lines of code before the breakpoint and a few lines of code after the breakpoint to help me jog my memory as to where this breakpoint actually is. What are some of the different variable names I might want to inspect? Then I can do things like display I. This, you can also do print I, by the way. This is actually going to show me the values of these different variables. Now, what's really, really interesting is this actually understands pointer arithmetic. So, for example, cur thread is a pointer to the current executing threads structure. So I can say display cur thread. Can't spell. Sorry, print cur thread. So I print cur thread, and you'll notice it says struct thread pointer. That doesn't tell me very much. So what I can do is maybe I want to inspect the values of cur thread. So instead of saying print cur thread, I could say print me the dereferenced cur thread. And look at that. It shows me the memory at that address. It's showing me the structure and all of the elements in the structure. So all of that pointer arithmetic works. So the question is, can you print function pointer addresses as well? Absolutely, because this understands pointer arithmetic. So it's exciting, right? I think it's exciting. All right, but that's not the coolest thing that you can do. So how did loud thread get called? That's a good question. Isn't it nice to be able to see a stack trace of how that particular function got called? So maybe you're running some code and you can't figure out why function X is running. Function X shouldn't be running. Who called it? Why is it being called? You can actually look at the stack, the call stack, and see who called it and who called that function. And to show the stack, we use BT. Now, this stack doesn't have much in it because this thread's brand new and it hasn't done anything yet. But as you can see here, that thread startup then called thread test, loud thread. So the highest number is going to be the oldest thing and the lowest number is going to be you. So there's our call stack. So that's really cool, right? So we can inspect our variables. You can even watch them to see when they change. You can also do things like looking at the call stack, all from Gdb. And when it comes to debugging these assignments, Gdb is going to be very, very helpful for you, because what's going to happen is if you just try to use printfs, you'll put your printfs in, bug goes away. You take your printfs back out again, bug comes back. And it's because of changes in the order of execution that this actually happens. All right. So to terminate, you can just type quit. And it says the program is running, exit anyways. Yes. And then if you go over here in the other terminal, you'll see that the debugger actually killed the program as well. So that's pretty cool, right? So we do have some Gdb instructions on the course website as well. And you're welcome to look over those or watch the video again. Pretty much everything that you have in regular Gdb, you also have here. Now, for those of you who want a graphical debugger, I am sorry, you are out of luck. We don't have a graphical debugger. I'm not sure you can connect DDD to this, and I haven't even used DDD in probably 15 years. It's like a graphical version of GDB. Anyways, you're kind of stuck with using command line GDB, but that's the way you should learn it anyways, in my opinion. Maybe I'm just old-fashioned in that way. So what we're going to do in the next episode is we will do a review of what this context switch looks like when you have threads that yield and threads that get preempted. And then I have a couple sample problems that we will go through. Those sample problems that we have are, so if you go on to Piazza here, let me just open up Piazza. I'll drag this over. So weird dragging between two screens with very, very different resolutions. So if you go into the extra sample problems and lecture content, and you scroll down, you'll see extra sample problems handouts. So if you actually go into that, and I know that's not what we have here. Let me go into this. Handouts. So the ones we're going to take a look at on Thursday is fork print and 2 threads. So take a look at those tonight, and then on Thursday we will go through them so you can get a feel for how questions about threads might actually run. And then possibly, if we have time at the end of the episode, we may also start talking about synchronization, which is a really, really important thing we need, because threads actually gives us some pretty bad consequences. So we will see you on Thursday, where we will do some more work with threads and then hopefully start looking at synchronization. So see you then.